Hello, and welcome to Zengit, uniting bright minds, forging brighter futures. Today, we're excited to introduce Mehregan Dor, PhD, an expert in navigation for robotic systems from Georgia Tech, who is actively looking for new opportunities. With over 7 years of experience in computer vision, estimation, and dynamical systems, Mehregan's expertise is shaping the future of precise localization and mapping. Tune in to the podcast to learn more about Mehregan Dor's groundbreaking work and his thoughts on the future of space exploration.
Hello, everyone, and welcome to another episode of Zengit Podcast, where we unite bright minds and forge brighter future. For today's episode, we have Dr. Mehregan Dor with PhD in navigation for robotic systems, with expertise in estimation, controls, and computer vision, and with over 7 years of experience in advanced localization and mapping. He is here to share his insights.
I'm actually a recent PhD graduate from Georgia Tech. It was a position that I held for almost 7 years here in Atlanta. I worked on many systems here, but mainly worked on implementing algorithms from the robotics community into the field of science in space, and that was kind of the vector of my research over the years here at Georgia Tech. Um, I also have a kind of a background from before that, mainly in the aerospace field. I did an undergraduate in Montreal at the Polytechnic School in Montreal, and then while I was doing that, I was like, well, okay, maybe it's an opportunity to also, when you do grad school, to also travel and to go other places in the world. And so I took that opportunity and then did my master's in France at the School of what's called ISAE. So it's the International School of Aerospace uh, and Aeronautical Sciences in Toulouse. And again, after that master's, I took the chance again at another international grad level study, and I went to Georgia Tech here in Atlanta, where I am currently. And right now, I'm working as a doctorate at the same school and lab that I did my PhD in.
Sounds great. So what are you gonna do after the PhD? Is there anywhere else you're gonna go?
So the horizon is large. There's a lot of opportunities. There's private industry, there's academia. So I'm on the lookout. I'm on the prowl for any opportunities that come up. Obviously, it's a very hot field of work. As I'm sure we'll get into it a little bit later, but the field of specifically of computer vision in which I work, it's extremely useful in all kinds of domains and applications right now. And take it from autonomous vehicles on the roads to trains and even drones, and now even in space. So it is a very commonly used, uh, you know, tool set. And so I think there's a lot of opportunities out there available if I had to choose one or the other. But yeah, that's pretty much it.
So thank you so much again for joining us, Mehregan, and I appreciate you sharing your, you know, uh, whole journey, academia, technical, and really let's start from the beginning, if you don't mind.
Mhm. Okay,
And
sure.
when you were, I don't know how far back can we go, and how far you would remember when you were 2 years old or 3 years old, or what did you want to be when you were a child? What was
Yeah.
it like triggering you, and then just the whole dynamic, if you don't mind sharing?
It makes for a maybe less interesting story, but it's definitely one that I think is truer. Since I was a very little kid, I thought of space robotics as something really cool just because of seeing it in TV shows and in cartoons, and later on in more like sci-fi stuff that I would like to watch. It was like it's a lot of interesting, the idea of like robots in space, and I really didn't think about it all that much. I was like, okay, this is interesting, but I didn't really know exactly what I wanted to do at that point, or what the track was to follow to even get there. Because everyone you have when you're 9, 10 years old, you have no idea exactly what are the steps one after the other that will lead you to that location. But as I followed suit with like engineering and STEM, it became clear that it's definitely a field that is kind of entrenched in mathematics, applied mathematics, And that was when it became clear that's the track I wanted to follow. I needed to get very good at math. I need to get good at programming, coding. I need to get good at presenting my results as well as somebody who would work on something that is somewhat innovative, experimental, research oriented. So, in that sense, it became clear that it's in the STEM direction was the way to go. And then again, at that point, you don't have an idea. You get to college and you think of yourself, okay, should I be a mechanical engineer? Should I be a engineering computer science engineer? Should I be an aerospace engineer? It's not clear exactly what the outcome of that decision is at that point. But at some point, I had a very interesting conversation with uh, an uncle of mine on my dad's side, and he said, "Well, you should just take the opportunity that comes to you that are available to you, and you see what comes out of that." In Persian, there's a famous saying where you say, "When you throw an apple in the air, it does 100 turns before it falls back down into your hands." So you don't have to make every decision as a final deciding factor for the rest of your life. There's multiple steps, and there's multiple ways to turn to one field or the other field, and you use your knowledge in the kind of broad sense. It's about building skills rather than building a specific uh, field of work per se as career. Career kind of comes along as you're building skills. It becomes a more solidified thing. And so in college, this is back in Montreal, I decided to go into an aerospace, kind of pure aerospace field. And I wonder at that point, I was thinking back at the moments when I was a kid, thinking, okay, robotics, space. These are like ideas that were in my mind, right? So at that point, I was looking at this interesting track. But obviously, aerospace itself is such an enormous field of work because it goes out, all the way from propulsion airplanes and space systems to telecommunications to avionics to mechanical devices, control systems. These are all the stuff that come together in the field to make the things that go fly and go very fast in the sky. But it is a field that's very much based and founded in the applied math procedures, and I think that's what first initially drove me to that direction because I knew there was a connection between the applied math and this kind of vague idea of robotics and applications in space that I had in my mind. And but as I followed suit, well, it became kind of even muddier and more unclear. The more you learn, the more questions you have, right? The more the horizon of questions opens up for you. So when got to the masters, I was like, well, what do I choose? And this was kind of the same question again. So at that point, I went towards a direction of doing a master's in space systems, and learning about systems is huge. If ever you work on, you know, uh, engineering devices such as like a spacecraft, or but I like to think of spacecraft as space robots, really, because they're essentially doing teleoperation at long distance or um, autonomous operation, and so these are like systems, and you have to study them in a systems oriented way, and then devise techniques and uh, you know procedures that kind of fit into that paradigm because it's about reliability and it's about autonomy. It's about how much it costs. When you build stuff, it costs money. It's not as if you can just park your spacecraft right there and go fix it on the side of the road. So that's a luxury you have on the ground when you're building autonomous car, but you don't have that when you're working with spacecraft. So that was another aspect that comes in the aerospace field is there is a much higher level of risk involved. So that was a question that became obvious at that point is okay, given this risk, what are the incentives for people to try reading novel, kind of immediately hot off the shelf kind of things, so cutting edge stuff. Um, and you immediately see in the aerospace field there's a bit of a reticence, kind of a diverse attitude about trying brand new things, and that's why when I got really interested in the ground robotics stuff, and the connection became more clear that if I wanted to really work on cutting edge stuff and implement it on devices on systems, there had to be some kind of connection to ground robotics, and that's when I followed suit with a PhD in in again aerospace, but much more oriented in the robotics applications. And when it became more clear later on what kind of research I wanted to do, I I I tried to bridge the gap between the robotics ground robotics community and the aerospace community by finding a subject that blended well in both applications. And so that's how I came through and thought of the idea of, well, what if we use these at that point was off the shelf algorithms, mainly in computer vision. One of them is called SLAM, so simultaneous localization and mapping. What I'm going to use these to perform navigation in space. And the idea is that, what was the word navigation? Navigation is the idea of localizing your robot, your autonomous device in its environment, making it aware of its environment and its own location within that environment by means of sensors, measurements, calculations such as filtering, and using that provided or that solved quantities for your specific task that you're trying to do. Either it's plan to perform a motion in that space, or grab a little sample of an asteroid and bring it back home, or if you're trying to do maintenance on large structures in space, such as the International Space Station, or if you're trying to do assembly of structures, something that's kind of scientific a little bit, or sci-fi a little bit. But on the horizon is the idea that we can build large structures in space autonomously. How do you localize your robots in space in that fashion? So it became clear that this is the need in the field at that point, because again, there was a reticence, there was a aversion to the idea of like, okay, well, we're gonna just take something from a different field and pop it in there into an aerospace application and risk it. So that's why you mostly at these points you have to go to the agencies, the national agencies, for that kind of funding for research of this kind of stuff, because the risk involved in it obviously is they will handle that better. So that's how I worked to fund my PhD. At that point, we wrote a nice proposal with NASA for what's called an early stage innovation study, and that helped fund my PhD and several actually other PhDs time at Georgia Tech. And this was a $500,000 proposal that we put together. So this was a kind of a broad sense of where I started from and where I ended up with. And I think there must have been something about this kind of vague idea of robots in space that kind of inspired the whole track. But at some point, at every step where I came to make a decision, it was very unclear in front of me what would be the outcome of doing this undergraduate degree, this graduate degree, going here, going there, changing schools, changing countries. That's also another aspect, right? So you want to be working at the spots where you can maximize the output of your work. And I think that's the most crucial aspect, is go to the places where people are the most knowledgeable or the most capable in the field that you work in. That's where I feel you have the highest impact in terms of your work. So yeah, that more or less sums it up for me.
I appreciate that. Thank you for sharing the whole process and everything. Was it at any point where you were like, I think I'm going down the wrong path? I think it's just so many things coming up. It's just like, I don't know. I mean, I'm good at figuring out what to do in space, but right here I'm running into difficulty. And
Absolutely.
so if you could get into that, and then how did you overcome it?
Obviously, when the going gets hard, that's when the questions become the most obvious about like whether you're doing the right thing, not doing the right thing. So at that point, initially, it was going through a very rigorous aerospace education kind of background, with all the field kind of exposed like that. Because again, as I said, there was mechanical engineering, there was electrical engineering, there was software engineering, there was all kinds of fields at the same time, and it's very overwhelming to be exposed to all these things at the same time and have some kind of idea in your mind of like, oh, this is the right thing to do. So I try to plan my life maybe no more than a year or two ahead. It seems a very short term procedure, but that allowed me to get through it. Is not to overthink about what are all the consequences of all these kind of small decisions more than over a year or two, because of all the randomness involved in it. So I did at some point, like get scared about like, okay, is this field gonna even like get me to where I want to go? That kind of stuff. And the way to overcome it is to set short-term goals, and then use those short-term goals to motivate yourself to continue. That would be the thing that was the most terrifying. Of course, in the PhD itself, anybody who's done a PhD could attest to this. The trials, tribulations, the difficulty going through qualifying exams, and writing your first thesis proposal, and then working out your first paper, and then publishing that and getting reviews back. And so those kind of events are always psychologically difficult, because you have to go through this self-assessment of whether you're good enough. This imposter syndrome of are you good enough in this field? Do you have what it takes to be here? Do you have what it takes to publish a publication that is worthy of the field? Right? And this kind of never really leaves the room. This is something that you always keep with yourself a little bit. It might be a sign of modesty and understanding the limits of your knowledge, and it's also a sign of there's like a bit of a peer pressure involved when you're in the field to do the best you can. And so you always have this constant questioning of, am I good enough for this? Is this the right thing to do? And during a PhD track, or like if you go into this kind of very specialized STEM direction, you always wonder whether the field you're working in will be relevant by the time you're finished your education, because the trends change in such a quick fashion. Um, if anybody knows about the field of controls, will attest that 10 years ago, fuzzy control was all the hot kind of talk all the time about fuzzy control in the field, and now it's completely changed. We don't really discuss it all that much. Now we have other other things that are really hot, and kind of on a daily basis you would get to discuss. In the conferences you would go and talk to people, they will bring that up all the time. And so these trends change very quickly, and so trying to stay relevant is another difficult and scary task. But in the end, in my opinion, there's always a niche for what you're doing. You just have to be at the right spot to exploit that skill set. um, and kind of build upon these connections, build projects, be proactive about putting projects together. And often what you start out working as a project will not be the one that you end up publishing in. So, or putting together into a company, or putting together as something that might grow bigger than what it is initially. So that's my kind of 2 cents about it. Is don't worry too much on the long term.
It sounds like a great strategy, actually. Um,
Yeah.
and I know timing is very essential when it comes to the research you do or the PhD, because how do you know? Maybe five other people are working on something similar or somewhere close. And from what I've heard in the past, like some people publish something like, oh my God, just somebody else did the research similar to this. And I have to go all over to go back to the beginning and start something new, or there's that
Mhm.
fear and not knowing what else everybody's doing, and did I waste my time focusing on this,
Mhm.
that kind. Did you ever face that?
I guess to some extent, yes. The field I worked in is, the niche of the niche. It's very extremely niche. There's like maybe a handful of people in the whole world who work on the same things directly. And you go to conferences, you go to events, you will meet these people, you will have discussions with them, you have conversations that are kind of, revealing about what kind of work they do, what direction they're taking. And I think instead of thinking of it as a constant competition between people, the best way to think of it is a collaboration. You need to bring people's abilities together. What they're really good at might not be exactly what you're really good at, even though you're working in the same field on the same kind of subject. There's a complementarity often about what they do and what you do. So it's less about being afraid of somebody grabbing your thing, or taking advantage of the kind of timing to do more than you do, than it is about kind of delimiting your project in such a way that you can get something reasonable out of it within the time frame that you have. And that's also the art of writing proposals, research proposals. You have to find the need within the field, the industry, or within the national agency that's funding it, and then use that need and tailor your project to that need. So that when you write a proposal, research proposal, or like a small business initiative or whatever it is, it answers to that need. And once you do that, even if there's people who are closely working on the same stuff, um, they might publish stuff or they might work like start a new thing. You always have some kind of assessment that you can base off of with saying there was this need, but I can work on this. I can maybe work on this other bit that they're not necessarily directly working on, and you can find a delimiting, I would say, set of things that you could work on that don't necessarily uh, overlap with what they're doing. Now, I'm saying this, but we also have the procedures of patenting algorithms and trying to publish papers and putting them on an archive to make it accessible to the community as fast as possible. That kind of stuff also exists in the field in STEM specifically, because there is this heightened idea of renown that comes with the work. You're working in the field of say robotics, and you have this new algorithm that you think might make a huge difference in the way things are run. You want to put it out there for the community. So the best procedure usually is to open source it and put it out there and make sure everybody knows about it as fast as possible. Like trying to skip a little bit over the whole peer review process of journals. It might take years for them to bring your paper to publication. So they will use something like a archive, which is a internet-based repository of papers, which don't really need the peer process review, and that allows them to put it out there immediately. Like here's what we did, here's the thing that we're working on, and you have to stay afloat of that. You have to like be aware that people are working on these things all the time. So not because it's a menace to your own work necessarily. It's just because it's important to stay relevant to the field in that sense.
So, because at one point I was working with like 25 PhDs, and each of them were very much experts in their own areas. And
Mhm.
sometimes when we had meetings, I had to help manage the egos between everybody.
Of course, of course,
That was one of the challenging parts, but the people skills helped to get
absolutely.
them to collaborate and work towards the same direction. Like you said, as long as people know and they're humbled enough to realize what their strengths are and their weaknesses, and then they could be very complementary to each other.
Correct.
And
I think it's a key aspect of research. The best research often is collaboratory, not individual. It's very seldom you will find a paper that is groundbreaking or changes the field, and you don't see 5 to 10 people working on it sometimes. So there's many people. Um, and so I think that's important. That's a testament to how collaboration can improve your own work. Uh, so staying in kind of that bubble of like competition between big minds, I think is not. First, I don't think it's healthy. I don't think it's good for you to view people who work on the same stuff as competitors necessarily all the time. I think as collaborators is the healthiest way to approach it. But yeah, that's
yeah,
that's kind of the idea.
and that's one of the part of one of our missions actually at Zengit. We would like to on this platform to get to the point where we could bring in all these uh, experts from different disciplines. And like you mentioned, as we go try to solve certain things now, I feel like, I always mention it to people, like I love this scientist from, like we talk about, like from the ancient times, that they were not just only a scientist, they were a poet and astronomer and mathematician and chemistry and multidisciplinary. And then when they looked at something, maybe it was from different point of view, and not just purely in one aspect they were good at, they would balance it off maybe or enhance it, having that diverse. And Professor Nader actually is one of those types. He's a bit of a poly, he says, yeah.
Mhm.
And Professor Nadi, maybe you want to share some, ask some more technical questions if you're available.
Thank you very much, Jack. Um, I'm poly something, but anyway, I have interest in many things. I was just wondering if Dr. Mehregan can specifically say what that robotics does in space, and then I have follow-up questions. Are you trying to detect other objects in space using some AI algorithms? And then if that's the case, tell me how you train it, because you don't have access to the space. Usually for these supervised techniques, then one of the problems that comes up is, where's my training set? So if I'm
Correct.
on the right track, please answer those questions. Thank you.
Yeah. So absolutely. I mean, so you asked what is it that we're trying to do. So there's two things. The word detection, I'm very careful about using the word detection, because detection, at least in the computer vision field, is about finding or trying to find the specific apparent objects in an image. Say you have a scene with or a living room, and you want to try and detect all the chairs in the living room, or all the seats, or all the cushions, or sofas, or whatever it is, right? Detecting objects in image sense, in that aspect, is about finding the features, a set of features you mathematically described, of course, of kind of characteristic features of these objects, and then detecting those. So we don't really do detection. What we do is we do tracking. So tracking is the idea that you have an object that's moving around, say an asteroid, a small body comet, a spacecraft, that you're looking at with a camera. And what you're trying to do is track something in its motion. For example, you're trying to track it across the image as it's going from left to right, or as it's rotating. And so it's about finding individual features on the spacecraft, or on the surface, and tracking those features. So it's a smaller problem. We're trying to, there are patches of information in the image that we're trying to track across time. And so there's a sequential temporal aspect to it. And then obviously there's the spatial aspect, the 3D geometry of it. The purpose of this is we want to localize the viewing camera. So this is the spacecraft that's observing the target. And then we want to also maybe reconstruct the shape of this target. So think of maybe one of the biggest problems we have in space is called space debris. So a lot of companies will come and launch the devices into space, low Earth orbit, medium Earth orbit, or geosynchronous orbit. And during the launch, they will use a multi-stage rocket. For example, a three-stage rocket. These different stages of the rocket, some of them will fall back down to Earth, and some of them will stay in space. And these parts that stay in space, they pollute literally the orbits that they were placed on. And so one of the projects that NASA is really interested in, European Space Agency is really interested in, is having autonomous vehicles go out there to try to identify these objects, grapple them, and then bring them back down into the Earth orbit to either disintegrate them in the atmosphere, or essentially safely land them, if that's possible even. The reason being, the more we do this, the more we launch into space, the more these orbits become cluttered with debris. So one of the tasks in that application of going and grappling a debris in space is the idea that you have to get there, and you don't know what this object is necessarily going to look like. Sure, at launch it had some kind of shape, some kind of form, and so you launched it in space. This is what you expect it to look like. But once you get there, this thing might have disintegrated. The color might have changed completely. Some of the bits might have broken off. And so you can't base it off of like a computer CAD model that I gave you to kind of track this thing. So one of the difficult aspects is once you get there, you have to be able to track things you haven't really seen. That's obviously a difficult problem to start with, just thinking about it in a procedural fashion. What is it that I have to track? And so one of the things we do is we look at these patches, we've got patch detectors in these images. So we take images either from existing missions that have flown that show other targets, such as a spacecraft or an asteroid, a small body, and then we build these networks to detect specifically these patches. And the question was, where does the data come from? Well, specifically, a lot of the data exists already. So NASA has flown multiple missions, for example, to small bodies. How do you then take that data? There's a whole lot of work of labeling and that goes into that to make it useful for supervised training. It's one of the works we did work on is called Astrovision, and it's specifically for using train networks for detection and description of surface features on small body objects such as asteroids or comets. And the biggest task was essentially building up this data set. So NASA has a data set called the Planetary Data System. And in the procedures that NASA do, they don't really think about the idea that, oh, somebody has to come and use this data to train an AI algorithm. So there was a big part of that is to, grab all this data, label it, make sure that it's correct. And then once we did that, then we can train these networks, which are mainly based on transformer architecture, which is the new hot thing now. And these transformer architectures will allow you to do detection and description of these features, these surface features. And then once we have these surface features, we can then uh, take the 3D geometry of the problem and solve it either in a filter-like fashion, like a sequential filter, or in a batch-like optimization, such as a smoothing problem. So there's that crucial part, which is the detection and of features. So you might say, okay, why don't you just take something off the shelf that already exists? So a lot of the algorithms that do image feature detection and description, they are trained on huge data sets of images that are created on the ground. So these are essentially, you can think of, there's several big data sets in computer vision industry at the very least that are used. These are like scenes within a house, a domestic kind of scene thing, or within in a park, or on the university campus, or in a street of cars driving by buildings, and so that's not necessarily relevant to the application. So it's often better. Well, this is still fundamentally not proven, but something that's really interesting as a research aspect is to take an existing off-the-shelf algorithm and then augment the data set that trained it to include data set that you also want to have it be sensitive to in its application field. So kind of a domain specialization of these algorithms. So that's what we did. We added a bunch of data that existed from NASA, from the planetary data system, and that improved the performance. We could see the improved performance of the algorithm. Obviously, the way you do these things is you take your data set, say your data set has 1,000 images, and maybe you take 2/3 of that data set, and then you use those 2/3 to train your system, and you withhold a third of that data set, so that you can then use that third to demonstrate that your system works better when you've done the training. The idea being you want to avoid what's called overfitting, of course. For those who are obviously knowledgeable about the field will know what overfitting is, but uh, in layman terms, the idea is you have some kind of uh, function that takes in inputs and it gives you outputs, and what you're trying to learn is this function. You have the inputs and you have the outputs, and you want to try to learn this function. You want this function to be quote unquote generalizable. So essentially, it has generality. I mean, so it has the idea that even with inputs it hasn't seen, it could still provide you outputs that are people harp on about this idea in the AI industry about whether these functions that you're trying to find these um, deep neural nets, for example, or what type of functions. They're essentially a representation of the function. Are they generalizable? So they cover the whole lot of the envelope of inputs that you may encounter, and if so, what are the outputs and what are they reasonable? Um, so we had to essentially use data that existed in the NASA databases, but obviously there's far fewer images of comets and spacecraft stuff than there is of like cats and dogs and chairs and desks on in these big kind of human environment based stuff. So, but that small addition of data still improved the margins of performance that we saw in the algorithm, and I think that's kind of revealing, right? There's a fundamental theory here that we haven't put down on paper yet. Why is it that this domain specialization necessarily improves your performance? Because one of the other issues is what's called explainable AI, people can't really explain what are the deep neural net layers doing. What is it that a neural net is learning? We have some intuition as to what we want it to learn, and with this procedure of like, okay, I'm going to train on these labeled data sets, and I'm going to make sure that the outputs of the network converge to these data set points that I've used. You will know what you want it to, and what way you want it to behave, but you can't explain what it is it's learning to do that, right? So this is a big problem. So we still don't have a fundamental theory of what we call explainable AI. So what are the middle layers of a neural net actually doing? So people have started looking at, and these are the natural language processing algorithms that exist out there. They're based on this idea of self-attention, and the idea you can have smaller networks that you've built in a recurrent kind of architecture. And the idea is that every layer has some effect, some kind of spatio-temporal effect that you can then use to improve the performance. So that people are trying to do that, to build these blocks of these bigger AI algorithms for this application of either it's tracking things over time, labeling actions, labeling. These are the things that kind of are very hot right now in the industry. But what we did there is to use this idea of image point feature tracking to then build the 3D geometry problem and then localize the camera in the scene. Hopefully that explains it. It was very left and right there a little bit, but I think I covered the base.
Thank you very much. That was very, very good. I just have one related question. Sorry. How did you feel about choosing transformers? Did you try convolutional neural networks with some other methods, or did you just say transformers are very popular? Why don't we just go right to that one?
Yeah, no, absolutely. That's a good point. So initially it was all convolutional neural networks. So we tried things like LFNet, L2Net. These are big convolutional neural nets. The idea is that specifically in our application, in the classical sense, we break it down into detection and description. So you see a point in an image, and you want to be able to describe it and detect. So detect means that if I give you another image that's very similar, I want to detect the same point that I detected in the first image. So that's a detection bit. You want a reliable detection. And then with that detection of the same point, you want to have data that describes what that point looks like in other images further down the line. So that's the reliable description part. And typically these are done in two separate actions. So you first detect and then describe. Now people have tried to build networks that do both of these things at the same time. But the idea of tracking across time has, again, this temporal aspect. The idea that data that you had from previous timestamp or sequence could be helpful for the next image that you obtain. So it's like typing on ChatGPT. You write a word and it gives some kind of response, or it's ready to give some kind of response. If you type another word, its response is going to be somewhat of a modification of the response it had before. It's not going to completely start new from something completely different. So that's the idea. There's like some spatial temporal continuity going on here, some kind of sequence of decisions, right? And so what we did is we realized that, yes, these convolutional neural networks are very good at individually detecting these features, at describing these features, but they're bad at matching or reliably describing them in a sequence. And that's what really matters to us, because you get an image sequence, such as in the camera looking at a target object, taking a sequence of images. You want to be able to detect the same point and have the same descriptor value across all these images. So that's why we went towards these transformer architectures, because they made sense. We tried the convolutional neural nets, and then we moved towards those afterwards.
Yes, that was a very good answer. Thank you very much. Predicting the next word in the LLM. So that's exactly
Correct.
what it was. Thank you so much. Appreciate it.
That's correct. Thank you.
Positive Nation impacting over 7 billion people. By doing positive acts of kindness around the world.
Every heartfelt plea. builds a future where every soul is free. From every corner of the earth to every single face, we're spreading kindness, leaving a loving trace. We're a positive nation, where hope lights the way. With 7 billion people, we'll rise every day. Through positive acts of kindness, let our voices sing. We're creating a world where positivity reigns. When the road is long and the night is cold, hold on to the love, let your heart be bold. In every act of kindness, in every care.
Join us and be a part of the Positive Nation community.
We're a positive nation, where hope lights the way. With 7 billion people, we'll rise every day.
Dr. Mehregan, I'm just really amazed by everything that you've shared. When I was like a kid, I watched this one episode in SpongeBob where they do exactly what you're saying. They go in the outer space and go detect those debris. It's just some weird stuff, and it made me realize that right now we are really living the future that I was once just watching in the television. And just a curious question: do you believe in aliens?
So, I mean, that's a good. That question has two aspects, right? There's a philosophical question and also at the same time a scientific question. Whether the idea that there's this vast space in which only this kind of tiny little spot of it had a very special, there's something very special about it that made it develop life and develop intelligent life. Moreover, not just life, right? So intelligent life, like that's another aspect, that's another roll of a die, right? You have these, you can think of, if you think of the existence of life as being some kind of probabilistic experiment, right? You can think of as these successive rolls of the die, right? So we had some kind of proto Earth that was very hot and that was, kind of uninhabitable, very alien to life, as to put it that way. That eventually cooled down and had water and bacteria, and this bacteria developed into more complex life, and then this life ended up coming out of the water and building. There was like vegetation, there was the animal kingdom, and all this led to at some point intelligent life coming around over billions of years. So it's essentially successive rolls of a die. Since you're saying that it could go badly. There could be an asteroid that hits the Earth, and suddenly, all life on Earth is gone over the span of some 4 billion years. And you think, okay, well, this experiment has been happening billions of times in space across multiple galaxies, multiple space systems. And you're like, okay, how unlikely is it that it's actually happened at least once, right? So the at least once, one other time. That's all you need is at least one other time, and then suddenly you have aliens, right? So that's the that's at least the scientific question, right? If I would like to believe that they actually exist, kind of out there. But yeah, I mean, that's one of the other reasons I got interested in comets and small bodies, asteroids, because of the huge impact that these have, right? And now you think about the impact a small asteroid collision on Earth could have on, changing the whole, environment, the biosphere. Some kind of event like that happened, and it became clear to me that there's more and more interest in NASA and other space agencies to make sure that we can detect these space rocks in space. Because what if they're headed towards the Earth? And right now there's a big problem, which is kind of I would say from let's say fridge size to a bus size piece of rock that's floating in space, we cannot detect until it's very close to Earth. So that is a very scary thing, right? It's like, oh, we don't really have the tech right now to detect these things in space. So how would you deal with these things, right? So one of the ideas are, if you had a fleet of autonomous vehicles that would be ready to respond in case one of these things got detected. What you could do is you could launch this autonomous robot, I would call it spacecraft, whatever you want to call it, and it could go near this object in space and slowly tug it out from its original orbit in such a way that it avoids Earth if it's actually a collision risk for Earth. But to do that, you need to have the ability to, when you get there, to identify the object, to perform robotic manipulation around it. And sometimes this can be at such a distance that we can't do it in a real time sense from Earth. So you can't have like somebody on the ground segment being like, okay, my robot should go a little bit to the left, a little bit to the right. These things have to happen in the closed loop feedback on board the spacecraft. And so you need sensors, you need algorithms that are predicated either in planning, navigation, so you can do these things in situ, as they say, like on the field. And so that's why I also got interested in the idea of applying these algorithms to that specific task of, detecting the motion of, or the reconstruction of asteroids, comets, small bodies, because these are actual risks and hazards for on the ground. There's a comet, I think it was about 10 years ago, that hit in somewhere in Russia. It was called the Chelyabinsk event, and it was about the size of a fridge. And that one, exploded in the air, in the atmosphere. It caused a lot of windows to shatter and that kind of stuff. Had it kind of impacted a little bit lower, it could have had a much more devastating effect. Threat exists, and so if we can have autonomy-driven technology that can, at least protect us in the future with these things. It sounds sci-fi-ish, but that might explain why the human race continues and why other aliens wonder if there are aliens based on this event. So if there are intelligent aliens, they hopefully at some point discover tech that saves them from comet impacts and asteroid impacts if they occur.
They should more worry about the comets than other aliens, you're saying, basically.
Yeah, exactly.
One of your most favorite movies, since you're talking about robotics and all this stuff, that you would say, is it Transformer? Am I?
Not quite. I'm more of the kind of very serious sci-fi stuff, like the Interstellars and the 2001 Space Odyssey, that kind of stuff, where I love the idea of humans and robots interacting too. I think that's a very cool concept. Humanizing robots is something new now, right? That sci-fi has explored for 30 years, 40 years, but I think that's always something that kind of is intriguing, is to when we build these systems that mimic human behavior, it suddenly makes them a lot more approachable for other humans, right? Humans who are not necessarily knowledgeable as in the field will be able to interact with them and have some kind of expected behavior. I think those movies are always fascinating, like TARS in 2001 Space Odyssey, TARS in Interstellar, and then 2001 Space Odyssey, I think it was called, what was that? I forget what the name of the computer is that the astronaut is interacting with. The idea that HAL, there you go, that's the one, HAL, right? HAL 2000.
No,
And
I told you.
That's why I'm poly. That's why I'm poly.
So that's the one that I'm sure as a kid when I watched that movie, I was like, okay, this is really interesting. Like, robots interacting with humans and assisting them in their tasks in space, because a lot of tasks in space are not meant for humans. They're not meant for like a human driver to do them. A lot of very kind of precision driven stuff that you can't really do with a joystick or with some kind of human system interaction has to be done by robotic systems. And I call them robotic systems. Spacecraft are already extremely autonomous. They have onboard control loops, they have sensors, they have all kinds of procedures and algorithms that are there. But the next step is really to bring all this ground robotics AI stuff into space, and that's I think is the field that I would love to work in, either in academia or in industry. Is if it ends up in space, obviously there's a lot of development that still needs to happen on the ground to make these systems reliable, robust, in that sense. So I would say, like, yeah, absolutely. In terms of movies, Interstellar is another really interesting one, because again, there's this robot that has to do these crazy tasks of doing these crazy computations within some amount of time frame, or being able to fetch something for them, or direct their spacecraft in a specific way when they're trying to get to a location. Things that a human being couldn't possibly do on the fly like that. And that on the fly behavior of robots in space is always fascinating to me when I watch these movies.
When when you were watching it, obviously, let's say the first time you were watching it, you were a child and you didn't have the knowledge you have today. Do you ever watch a movie now and you're like, that's not really technically possible?
Yeah.
Where you catch them.
I mean, especially when it's like, crazy calculations that in the plot of the movie, it was a big uncertainty. And then suddenly the computer can just calculate this probability for you out of the blue. Like, oh, this is the probability of you landing on this thing or you being able to find this thing. Yeah, those are always like, well, okay, how did you do that? How did you figure that bit out? The idea that so this is an interesting question, I think, fundamentally, because like philosophically too, these systems have a lot of information, right? Like you can think of ChatGPT, you can type something in and it'll find it for you. You can even give it take it as a challenge, find something that you think is completely out of the blue that it would never know, and then you try to put that in and it still finds some connection to it, right? So these systems would at some point have a very deep connection to the amount of information out there. But whatever information these systems have is never more than what humans actually have, right? So like it's always replicating something that we already have as information. It doesn't generate new data. It doesn't generate new information. It's doing some kind of, what I would call some kind of convex, combination of points, of data points that you have within the space of training it was trained on. So at the end of the day, it shouldn't be able to do things that at some point humans are not able to do, right? If you just put the right team together, or if you put the right people there, you ask the right experts, they should be able to do the same tasks. It's just the availability of that information at your fingertips. So whenever in a movie they ask the computer to do something that none of the humans there can do, none of the humans have the ability to do. That's like you're like, all right, that's interesting. That's kind of a new one there.
Well, whatever sells more popcorn,
Mm-hmm.
that's what they look at. No, but it just interests me, how, when somebody makes a movie, I'm like, okay, do they have really some scientists on the, advisory here? They talk to some NASA people or whoever that, hey, this is the plot we have, and is it possible? There are a couple of YouTubers that try to kind of analyze the movies, and I mean, they don't do it like too much on technology, but some of them primarily on some of the special effects and everything, and they're like, yeah, this is not exactly in the real life is like this, versus they kind of debunk things, which is interesting.
Mm-hmm. Yeah, absolutely.
I think they have. The black hole doesn't look like a hole in a sink. It actually has that event horizon now because they talk to some physicists. But the notion the sound disseminates in the space in the movie, it's wrong because there's nothing to move those molecules. So it gives you the impression that something is going on, as Star Wars and so on. So yeah, they have their take on that. I just have a curiosity question. Are you interested in NORAD data, and does that help you, or are they? I'm sure they're interested in your work, but I think there's a level of confidentiality. Just if you could answer that.
So I believe NORAD data is all ground-based observations, mostly of spaced objects. So these are essentially either radar or direct visible light spectrum or infrared spectrum observations of things in orbit. These are not necessarily in line with my work, because my work is more about proximity operation to objects. So this is like autonomous vehicles when they get close to their target. This is once the object can be resolved in the image to high precision. So the apparent size of the object is large in the image. But there are Earth observations that are based like that could be used in that sense, because they very precise observations, very close-up observations. But typically in that case, a lot of the unknowns that we have in the application, which is this camera located, or which direction is it viewing, those are already solved because you have these antennas or telescopes that are already looking at these targets in space. So they're already resolved in terms of orientation and location. What we try, the idea is that we want to do simultaneous localization and mapping, typically for this kind of autonomous application. If that makes any sense. So I'm sure
Yes.
I'm sure there's still interest in it. I'm sure people will. I mean, I've been approached by AFRL, the Air Force Research Lab, for a lot of the work that we've done. We've been approached by the ONR, the Office of Naval Research, that also work on kind of these space rendezvous or either space proximity operation, applications, and they're interested in our algorithms because they have a very direct use, in kind of in space. And one of the things you don't want to do in these kind of like more military applications is you don't want to have a sensor on your spacecraft that gives away where you are and what kind of frequency you're using, that kind of stuff. So you want to be kind of stealthy in the way you detect and perform this operation. So mainly using visible spectrum cameras is the way to go, and specifically monocular, so no stereo. And so because of this aligns with our work, there's been quite a bit of interest in terms of the uses that it could have. Specifically from AFRL, we got a lot of interest. Yeah.
Thank you.
I mean, all the stuff that you're talking about and your research, it's, to me, you could apply it not only in space, not only on the ground, not only in the ocean, right? You're talking about, basically, scanning. So have you looked at other sectors, or is it your appetite primarily space? Or
Actually, I have actually. That's a good question. Recently, I've started working a little bit more on. I'm doing this kind of consulting, contracting that I'm doing with a startup who works on, pose estimation for humans for a specific application of, in the medical field. And what we had to do was interesting because there's a lot of overlap between the kind of use of their application and SLAM pipelines that I've developed and that kind of stuff. So we're trying to bridge that gap in that sense too. There's a lot of work that's gone into pose estimation for humans, like stick models that have been extracted from 2D images and 3D images, 3D pose estimates obtained from those 2D images. That kind of stuff has been worked on a lot. But because it's so much overlap with what I've already worked on, the application was almost immediate. So one of the interesting things is, if you apply for a job in the robotics field or in the aerospace field, one of the things they will ask you is like, oh, well, did you work more on robotics or aerospace? I find this one of the most irrelevant questions because really it's not about what field you worked in. It's about what kind of skills you have in terms of, the algorithms you can implement, the mathematical, analyses that you can perform, kind of the applied math that you can put together, the kind of first principles approach. You have a problem. I give you a whiteboard and the problem. Can you start from first principles and work the whole thing out? If you can do that, it doesn't matter what field application it is that you're gonna kind of butt up against. That you're gonna be able to find your information, read a couple of papers, get knowledgeable about most of the stuff that's going on in that very specific kind of niche thing. If you have enough time, of course, that's the other aspect. With enough time, anybody can get there. It's just, if somebody has the skill set for that field, then it's enough, right? You don't have to call it, a robotics PhD or an aerospace PhD or, electrical engineering PhD when it's really about the skill set. So I use some of this knowledge in the space to implement these kind of pose estimates for human pose estimation, which is interesting because it's used in the medical field a lot, and more so now. Yeah.
without giving too much away, and I'm sure you're under various NDAs and everything. Are you designing a mini spacecraft that will travel within the body and bypass not the asteroids, but whatever fat cells or anything else, try to get to the
No, it's actually much simpler than that. It is a device that would help physicians and practitioners, uh, you know, identify uh, characteristics of somebody's gait, somebody's like motion essentially, and this can be done with using any kind of camera specifically. So that, I mean that's to some extent what I can reveal is just more or less that you're trying to do analysis of somebody's gait, more or less.
That's pretty cool. Professor Nader, what was the name of that movie? You know, he's so knowledgeable about the movie industry. The one that
Which one?
the one that they traveled within the body, you know, one of those sci-fi
Oh,
ones.
yeah. Raquel Welch was in that. That was long time
Fantastic
ago.
A
Yes,
Voyage.
long time ago.
I had
Oh, that's the
just
first
had
one.
my first tooth coming out through my gums. I think I know which one you're talking about. It was
Fantastic
really
Voyage.
that's
Fantastic
right.
Voyage.
Fantastic Voyage. It was a very cheesy sci-fi. It was really nothing compared to what you see right now. Yes, that was the case. They do have pills that you can take, and I think they have put some cameras and some Wi-Fi communication, so you can, or actually maybe store it in a flash and somehow you extract it from your system, see the images. But they have worked on that. This is not new. It's just the problem is it's very invasive. And what if things go wrong? And they are working on that. That's just a very good point. Yeah. Just a multiple choice question for all. How many galaxies are there? So I'm going to give you billions, hundreds, or trillions. What's
Should I
the
go
correct
first?
answer?
Should I go first?
Yes, go ahead.
I think it's in the trillions. If it's the
It's
number of
correct.
galaxies. Yeah,
It's correct. And
yeah,
therefore, when you were talking about the probability of having exoplanets meaning planets that are very similar to us in terms of atmosphere, being as much distance to their star, sun. So if you multiply that, you could see that the probability of other beings be there, it's astronomical in terms of
yeah.
the chances. So I just wanted to share that with you. It's really crazy that there are trillions of galaxies, and each galaxy has trillions or billions of stars. And just, it's unbelievable. It just shows how we are.
Correct.
Anyway,
And an experiment, however improbable, if done enough times, will yield outcomes that are unexpected, right? It's kind of
yes.
what explains the idea of miracles, right? So,
So we're not alone. There's a Jacques somewhere in those galaxies.
You know that? Remember that movie?
oh, that one's
Yes.
great. Yeah, that's a
Who
great
was
one.
in there?
I think it's
Uh,
Jodie Foster, right? Jodie
Judy
Foster is in that.
Foster. That's right. Good,
that's right.
good.
Very
But
good. I'm very impressed.
Also,
there
Matthew
was a
McConaughey, I
line.
believe. Matthew McConaughey, Jodie Foster.
Okay, that's
Also,
right.
mm,
Oh,
Very
wow.
good.
Yeah.
Excellent. That's very
There
good.
was there was a sentence she said. There was a line in there, and
Yes.
that was, I think, the most famous part that I guess her dad told her or something like that when she was always staring at this, you know, space and sky, and she said it would be a waste of space if there
Yeah.
was nobody
yeah,
else. Do
correct.
you remember that? And with what
Yeah,
you're saying, it makes sense,
Yeah.
right?
And the interesting thing is that since everything started from what we know from the bottom of the oceans with single cells and multiple cells, and they developed into more complicated marine life, and then they came out, and they one day went, most of them went back in. That's why the
right.
whales have those extra bones. It's really funny, the cycle. It did it similarly happen in other planets, and they will be just equivalent to us in terms of progress, maybe further ahead in time, but very similar to us. They don't have fewer carbon cells. We're all, you know, stardust. If you think about it, the carbon in you
Right.
came from millions and billions of light years away. And the gold that some of the ladies right now are wearing, that was created by fusion of heavier elements. And now you get it in this planet that traveled all around the galaxy. It's really fascinating when you think about these things.
Right.
So
It's funny you brought up Contact earlier. Contact, I think the script of Contact was written by Carl Sagan, actually. He was the one who wrote
oh,
the scenario.
nice.
And Carl
Nice.
Sagan obviously famously talked about star stuff or stardust as
Yes.
being the kind of formation of everything, we know. The famous
Yes.
pale blue dot kind of commentary that he made about how everything, all the great tyrants of the world, all the, history, all the great wars happen on this little tiny little dot that you see in this image. And like it's humble, and also it opens up the idea that, well, if this is just one tiny little dot and there's so many of these tiny dots out there, then the probability of these things not happening elsewhere, and then us having this kind of very I guess human centric view of the universe, as, oh, here we are all alone and we're observing outwards, or maybe some people are observing from outwards towards us, right? So I think that's an interesting idea too, that these kind of sci-fi movies explore, and I think that's because it was based mainly on a lot of scientific observation. I think another really cool thing is, people. I think it's science in the very general sense, is something hard to grasp for most people who don't have the training or the background. And I think as a almost a duty for people who are trained in STEM to be able to make it palatable, to make it more interesting. And one of the things, a lot of 16 to 20-year-old kids will say, "Oh, I hate my science class. I hate my math class. I hate this kind of, dry and rough and kind of boring things." Is that they don't realize that with their scientific knowledge, they open such a broad, sense of unknowingness, right? So like I think that by knowing things about the universe, it'll make it less mysterious. But in my opinion, it makes it more mysterious because the horizon of the questions it opens up is always bigger than the radius of questions we've. So think of it as a circle, right? So we have the radius of a circle as being the extent of our scientific knowledge, of our understanding, and then the area of this circle being the questions we've answered to this point. When the radius increases a little bit, the amount of questions increases, quadratically, the square of it. So uh, there's always more questions when there's a little bit of scientific improvement, because it opens up this whole swath of, oh, we didn't even think about what the implications of answering these questions was. And so to me, having more scientific knowledge is not boring or less interesting. It makes the universe more mysterious and more interesting. And our tech to a medieval peasant would look like magic. Well, the same thing we could think of if we went forward 1,000 years. If we saw technology from 1,000 years from now, we think it's magic. Well, that magic should be mysterious and inviting for us, right? In terms of us trying to attain it. And I think it's important to pass that on to the younger generation and make them kind of interested in all that by making it more palatable. And I think as scientists, it's important to take that project on as a form of duty, right? So more of giving back to the field that kind of nurtured our success. So that's the idea.
That is exactly, again, you just like speaking on our behalf. This is exactly part of our mission. We want to make this so attractive, as you said, palatable, and also really sexy for all this, you know, young generation to, as you said, we're just scratching the surface. We're not even there where we're like, okay, we're 70% there. The more we dig in, I mean, we learn about the oceans and it's right underneath us. And, the moment we start diving into it and getting into it, and we're like, wow, we're just learning about the humans, the same thing. So much
Right.
technology has evolved so much, and we have discovered with everything surrounding us, we're not there yet, right?
Yeah, correct.
And I think that curiosity, like you said, is what drives everybody continuously forward. And
Mhm.
this collaboration, my hope is with our platform, we could accelerate this process and collaborate
Mm.
and get people to share more. And that's going to, just listening to you is going to trigger a lot of things. And the impact of that is amazing. What we can.
I hope I have that effect. I've tried to make that a kind of somewhat of a goal in my life, to kind of pass on the torch. If
You
like
you
in my
sure
free
have
time.
done already. Mela is motivated to go watch those movies. I just noticed that. No, but this is good. Thank you so much. I think there's so much we want to talk to you about, and I think we want to invite you back. And
Okay,
I know you speak multiple languages, so maybe we could do French next time.
absolutely,
And
absolutely.
to get Professor Nader to share some of his poly abilities, and it's amazing. You see, he comes up with this uh, great questions, and it just
Absolutely.
spices everything up. Well, thank you so much, Mehregan, for your time. It was a pleasure in allowing us your time.
All right, Dr. Mehregan Dor, thank you so much for answering those weird questions in my mind. And with today's news about UFO sightings and everything else, I know their questions on their mind are answered too. And Dr. Mehregan Dor, just to sum up our today's discussion, what are your advice to today's generation?
I would say make it a. So I would say, people. Some people hate. They can say, "I hate learning. I hate classes. I hate school. I hate that kind of approach to kind of learning because possibly they've had kind of bad experiences in their life as kids or teenagers going through the kind of educational schooling system. I would say try to relearn to learning. Liking to learn, I think, is one of the most crucial aspects of self motivation when you're trying to get into a field. And obviously, that means working on something you really love working on. It's kind of self-sustaining as a feedback loop, and I think that's what's important: is work on something you love and try to like learning more about it, or learn to like more learning. So yeah, that's my advice.
All right, thank you so much, everyone, for tuning into another Zengit Media podcast. And I'm sure your minds are full right now with all those thoughts and information. Thank you so much, Mr. Jakfar. Thank you so much, Professor Nadir. And thank you so much, Dr. Mehregan Dor.
Thank you.
Bye bye.
Positive Nation impacting over 7 billion people.
In a world so vast,
By doing positive acts of kindness around the
every
world,
little gesture, every heartfelt plea builds a future where every soul is free. From every corner of the earth to every single face, we're spreading kindness, leaving a loving trace. We're positive nation, where hope lights the way. With 7 billion people, we'll rise every day. Through positive acts of kindness, let our voices sing. We're creating a world where positivity reigns. When the road is long and the night is cold, hold on to the love, let your heart be bold. In every act of kindness, in every care.
join us and be a part of the Positive Nation community.